All right, let's dive into something, well, incredibly fundamental today. Stuff that's quite literally holding our physical world together. We're doing a deep dive into chemical bonding.
Yes, and we've been looking through your notes, some key excerpts on this. It's really core chemistry, isn't it? Understanding these invisible forces that, make things behave the way they do at the atomic level.
Exactly. So our mission here really is to unpack the main ways atoms connect and, crucially, why they connect. And hopefully pull out some insights from this material to, you know, really get a handle on the amazing variety of matter we see all around us.
Absolutely, because it's not just which elements are in something. The way they're linked up, the bonding, that's critical. It dictates almost everything about a substance.
It's like the universe's basic construction manual. So let's start right there. The definition from the sources. What exactly is a chemical bond?
Okay, so at its heart, a chemical bond is basically a strong, attractive force. A force that holds atoms together in a substance, whether it's a molecule or a larger structure. It's the glue.
The invisible glue, yeah. And how that glue works, how the atoms stick together, that determines the structure. And the structure then dictates, well, everything else, right? Melting point, conductivity, solid, liquid, gas.
Precisely, it's the blueprint. But how is any of this stuff held together? How do those individual atoms we've been talking about actually, connect to make all these different molecules and compounds?
That's the fundamental question, isn't it?
Yeah.
It's the difference between knowing the alphabet and being able to read a book, really.
Mm-hmm.
Understanding the elements is step one, but understanding how they stick together, the chemical bonds, that's how you start to understand why matter behaves the way it does.
Exactly. And that's our mission in this deep dive. We're going to dive into those strong, attractive forces between atoms and the chemical bonds. We want to get to the bottom of why different elements form different types of bonds, understand the absolutely crucial role that electrons play in every kind of bond, and learn the system we use to actually name these compounds once they're formed.
Right.
So think of this as building directly on your understanding of electron configurations and where elements sit on the periodic table. We're seeing how those basic properties we just covered totally dictate how elements link up.
How they interact.
Yeah, how they interact to form the substances all around us. It's where the static map of the periodic table really comes to life.
What's fascinating here is that the entire drive for atoms to bond is really about achieving stability. If you think about the noble gases, right? Group 18.
The unreactive ones.
Exactly. They're already incredibly stable. They don't react much. Lewis' theory helps explain this by saying atoms bond to gain that same stable electron configuration as a noble gas.
The noble gases, the ones with that perfect, full outer electron shell. So atoms bond because they want to look like them electron-wise.
Precisely. And for many elements, especially the main group ones, this stability is achieved by getting 8 electrons in their outermost shell. That's the famous octet rule.
8 is the magic number.
It often is. Atoms will transfer or share valence electrons until they hit that magic number 8, achieving a closed shell.
So the whole game is getting to 8 valence electrons.
For many, yes. And you can often predict how an atom will try to achieve this just by looking at its group on the periodic table.
Yeah.
You take metals in group 1A or 2A, for example. They only have 1 or 2 valence electrons.
Easier to lose them.
Much easier for them to give away those few electrons to get down to the stable, full shell that's already there underneath, left over from the previous period.
While nonmetals, especially in group 6A or 7A, they're just a couple of electrons short of that octet. So for them, it's much easier to gain electrons to fill that outer shell.
Exactly. And whether an atom tends to gain or lose, or even how strongly it pulls electrons in a bond, is quantified by a property called electronegativity.
Electronegativity. Right, that's how strongly an atom attracts electrons.
Electronegativity, or EN, is a measure of an atom's ability to attract electrons to itself within a chemical bond. It's essentially how good it is at winning the electron tug-of-war when it's connected to another atom.
Okay, so if you have 2 atoms trying to bond, their difference in electronegativity is the crucial indicator, like how different their pull strength is.
Absolutely. The difference in electronegativity between the 2 bonding atoms is what fundamentally determines what type of bond will form. You see, metals generally have low EN10. They don't pull electrons strongly.
They tend to give them up.
Right. While nonmetals have high EN, they have a strong pull. They want to gain electrons.
And that range of differences in EN is what leads to the different ways electrons behave when atoms bond. Let's walk through those main types.
Okay, so when you have a very large difference in electronegativity, typically between a metal, low EN, and a nonmetal, high EN, you get ionic bonding.
So the atom with the much higher En basically just takes the electron from the one with much lower En. A complete grab.
That's right. It's an electron transfer, not sharing. The low En metal gives one or more valence electrons to the high En nonmetal. This transfer creates charged particles.
Ions.
Exactly. The metal atom that lost electrons becomes a positively charged anion, and the nonmetal atom that gained electrons becomes a negatively charged anion.
And the bond itself isn't a physical connection like a shared pair. It's the powerful electrostatic attraction between these oppositely charged ions, like tiny magnets holding them together in a crystal structure.
That's a perfect analogy. And
And
this process dramatically changes the size of the atoms. Gadgets are always smaller than the neutral atom they came from.
because they've lost their outer layer.
They've lost their outermost electrons, yeah, and the remaining ones are pulled in tighter by the nucleus. Anions are larger than their neutral atom because adding electrons increases repulsion between them, spreading them out, and often filling a new energy level.
Fascinating. Losing electrons makes you smaller, gaining makes you bigger. And I remember the material mentioning isoelectronic ions. Those are ones with the same number of electrons but different elements.
Yes, exactly. What's interesting is that in such a series, the size decreases as the atomic number increases
Why is that?
because the nucleus has more protons, a stronger positive charge, pulling those same 10 electrons tighter.
Okay, so even with the same electron count, the nuclear charge makes a difference in size.
Got it.
And how strong is that magnetic pull, that ionic attraction in the solid state? Is there a way to measure that?
There is. That strength is measured by something called lattice energy. It's the energy change, usually released when gaseous ions come together to form this solid ionic compound. It tells you just how tightly those ions are packed and held in the crystal lattice.
Right. And the material points to a formula, E equals K Q1 Q2 R. What does that tell us, simply?
Well, it basically shows us that the strength of the ionic attraction, the lattice energy, is strongest when the charges on the ions, Q1 and Q2, are large, and when the distance between the ion centers is small.
Makes sense based on static electricity, right? Coulomb's law.
Exactly. Bigger charges pulled closer together mean a stronger force. So highly charged, small ions form compounds with very high lattice energies, very stable crystals.
Got it. Big charges, short distance, strong ionic bond. And it's not just single atoms that become ions, right? There are those groups, polyatomic ions.
Absolutely. These are groups of atoms covalently bonded together that carry an overall positive or negative charge, like ammonium, NH here, or nitrate, or sulfate. These polyatomic ions function as a single unit in ionic compounds, attracting oppositely charged ions.
So you name them as a unit.
Yes, and knowing the common ones is essential because they're incredibly prevalent in chemistry. You really just have to memorize the main ones.
Okay, so ionic bonding. Electron transfer between metals and nonmetals driven by a big En difference, resulting in strong electrostatic attraction between ions. What happens when the En difference isn't so large, typically between two nonmetals?
That's usually where we see covalent bonding. Instead of one atom taking electrons, they share pairs of electrons to achieve their stable octets,
Sharing is caring in the nonmetal world, and they can share one pair for a single bond,
or two pairs for a double bond.
or even three pairs for a triple bond. Wow.
Exactly. Double bonds are common between atoms like carbon, nitrogen, oxygen, and sulfur. Triple bonds are most often found between carbon and nitrogen atoms, like in the cyanide ion or nitrogen gas in uros.
So sharing multiple pairs helps atoms satisfy their octets when just one pair isn't enough.
Precisely.
And just like ionic compounds have lattice energy as a measure of strength, covalent bonds have properties like bond length and bond energy, right?
They do. Bond length is pretty intuitive. It's the average distance between the nuclei of the two bonded atoms where the energy is lowest, most stable. Generally, bond length increases with the size of the atoms forming a bond. Bigger atoms, longer bond. Makes sense. And bond energy. Bond energy is the energy needed to break that bond, specifically to break 1 mole of those bonds in the gaseous state. It's a direct measure of how strong that particular covalent bond is.
More energy needed, stronger bond.
Correct. And the material points out an interesting trend. For bonds between hydrogen and elements going down a column, like HF, HCl, HBr, HI, the bond strength actually decreases as you go down the column.
So HF is stronger than HI, even though iodine is bigger.
Yes. The larger size means the shared electrons are further from the nucleus. The overlap isn't as effective, so the bond gets weaker and easier to break.
Okay, so larger size can weaken a bond in that case. Now, sharing electrons is the core of covalent bonding, but is the sharing always perfectly equal?
Good question. No, it isn't always. And that brings us to polar covalent bonding. This occurs when electrons are shared, but not equally, because there's still a difference in electronegativity between the two bonded atoms.
Not a big enough difference for a full transfer like ionic, but enough to skew the sharing.
Exactly. Enough for one atom to pull the shared electrons closer to itself more of the time.
So the atom with the higher En hogs the electrons a bit more. It becomes slightly negative and the other slightly positive.
Precisely. The electrons spend more time closer to the more electronegative atom. This creates an uneven distribution of electron density. We call it a partial negative charge, written as delta minus, on the more electronegative atom, and a partial positive charge, delta plus, plus an all, on the less electronegative atom.
And you see those little arrows sometimes in diagrams.
Yes, the dipole moment arrow. It points towards the more electronegative atom, showing the direction of the electron pull, the shift in electron density. This creates a dipole moment in the bond.
Okay, so unequal sharing creates these partial charges and a dipole. Why is knowing whether a covalent bond is polar or nonpolar so important? What difference does it make?
Oh, it makes a huge difference to the properties of the molecule itself, especially how it interacts with other molecules. Molecules with polar bonds often have significantly higher melting points, higher boiling points.
Like water.
Like water, exactly. It's also why they tend to be more soluble in water, which is itself polar, and have lower vapor pressures compared to nonpolar molecules of similar size.
Because those partial positive and negative ends can attract the opposite charges on neighboring molecules?
You got it. That unequal sharing allows molecules to attract each other through these partial charges, creating stronger intermolecular forces, the forces between molecules.
Okay, so we have ionic bonding, electron transfer, big En difference, metal-nonmetal, covalent bonding, electron sharing, small zero En difference, non-metal, and polar covalent bonding, unequal sharing, moderate En difference, non-metal. Are there other major ways atoms connect?
Yes, there's metallic bonding, which describes how atoms bond together within a bulk sample of a metal.
Ah, the famous sea of electrons idea? Is that accurate?
It's a useful model. The material describes it as a situation where the valence electrons are shared among all metal atoms. They aren't tied to any single atom or pair of atoms.
They're de-roaming.
They're delocalized, yes. They can move throughout the entire crystal structure of the metal. This delocalization is why metals are such good conductors of heat and electricity. Those electrons are free to move and carry charge or energy.
That makes perfect sense. Okay, and there was one more specific type mentioned in the sources. Coordinate covalent bonding. What's that about?
This is a special case of covalent bonding. Electrons are still shared to form the bond, so it's covalent. But both electrons in the shared pair come from just one of the bonding atoms.
Wait, so one atom provides the entire electron pair for the connection, the other atom just accepts it?
Correct. This often happens when a molecule or ion that has a lone pair of electrons, we call this a ligand, forms a bond with a metal ion, which often has empty orbitals available. The ligand effectively donates that lone pair to the metal ion to create a shared bond.
And the material mentioned vitamin B12.
Yes, as an example where ligands are bonded to a central metal ion using this kind of coordinate covalent bond. It's very important in coordination chemistry and biochemistry.
Okay, that's a specific but clearly important type of bond, especially in complex molecules. So we've covered why atoms bond that drive for stability, the octet rule, and how they bond transfer, different types of sharing, the sea of electrons, even coordinate bonds, all driven by that key property, electronegativity. Now, once we've formed all these incredible compounds, how do we actually talk about them clearly? How do we name them?
And that brings us to the absolutely essential language of chemistry, nomenclature or systematic naming. It's critical. I mean, if you're given a chemical formula, you need to know its name. And if you're given a name, you need to be able to write its formula correctly. Communication depends on it.
Right. This is why we can't just use old-fashioned common names like sugar of lead or blue vitriol. They sound cool, but they could be ambiguous or don't tell you anything about the actual chemical composition.
Exactly. We need the systematic names like lead 2 acetate or copper 2 sulfate. The material outlines the rules for systematic naming, and they depend on the type of compound you have. Let's start with binary ionic compounds, just two elements, a metal and a nonmetal.
Okay, what's the rule there? Does it matter which metal?
It does. If the metal typically forms only one kind of ion, like sodium, always Na, or calcium, always Cal, from groups 1 and 2.
The predictable ones?
Right, you just name the metal canication first, then name the nonmetal anion and change its ending to idagate. So NaCl is sodium chloride, Mg-Brero is magnesium bromide. Simple.
Okay, but what about metals that can form ions with different charges, like iron can be Fe or Fu? or copper?
Good point. For those, you name the metal cation, but you have to indicate its specific charge, its oxidation number, using Roman numerals in parentheses right after the metal's name.
Yeah.
Then you add the non-metal anion with the "-ide" ending.
So FeO oxygen is usually -2, so iron must be +2.
Exactly. So it's iron 2 oxide. And the FeODOers, oxygen is -2, 3 of them make -6 total charge. So the 2 irons must be +6 total, meaning each iron is +3.
So iron 3 oxide. Okay, the Roman numeral specifies the charge on that specific metal ion in that compound.
Precisely. And there are a couple of quirks mentioned, like mercury I always exists as a pair, Hg, so the name mercury something. And some transition metals like zinc, zinari, and silver as ion usually only form one common ion, so you typically don't need the Roman numeral for them, even though they're transition metals.
Little exceptions to remember. Okay, that covers binary ionic. What about ionic compounds that involve those polyatomic ions we discussed earlier, like sulfate or ammonium?
Much simpler, actually. You just name the polyatomic ion, then you just name the polyatomic ion. That's it.
No iodide ending.
Not unless the polyatomic ion itself ends in -ate, like hydroxide,
Yeah.
OEO, or cyanide, CNFone. But for things like nitrate or carbonate, you just use the polyatomic ion's name. Again, this is why memorizing those common polyatomic ion names and charges is non-negotiable in chemistry.
Right, so NHSEl is ammonium chloride, nanoaero is sodium nitrate. Makes sense. And finally, what about naming binary covalent compounds, typically between two nonmetals? The material says we use prefixes here.
That's right. Because you have different ratios, like CO and co-arrows, you need to specify how many of each atom. You use Greek prefixes, mono, di, tri, tetra, penta, etc., to indicate the number of atoms of each element present in the molecule.
How does that work exactly?
You name the first element using a prefix only if there's more than one atom. The prefix mono is usually omitted for the first element. You name the second element always using a prefix, even mono, and change its ending to -ido.
Okay, so CO, carbon is first, only one, so just carbon. Oxygen is second, one atom, so mono prefix and "ide" ending, carbon monoxide.
Perfect. And co.
Still carbon first, only one. Oxygen second, but two atoms, so prefix and "ide" ending.
Iron dioxide.
Exactly. All right, and decone. Okay, nitrogen first, two atoms, so prefix. Dinitrogen, oxygen second, one atom. Monoxide? The nitrogen monoxide.
You've got it. Those are the basic rules. And the material also mentions there's a whole other set of rules specifically for naming common acids, which makes sense as they're a distinct and important class of compounds.
Right. So mastering these systematic rules for nomenclature is absolutely fundamental. It's not just memorization, it's like learning the grammar of chemistry.
It really is. It's how you participate in the conversation, how you understand instructions, how you read labels. It's crucial.
So for you, the listener, as you navigate the start of your chemistry journey,
Yeah.
why is digging into how atoms bond and how we name the results so crucial? Why should you really focus on this?
Because it allows you to start making connections and predictions. Understand the bond type, whether it's ionic, covalent, metallic, tells you so much about the properties you can expect from a substance. Is it likely to be a solid crystal with a high melting point, like salt? Ionic. Or maybe a gas or liquid at room temperature with a lower melting point, like methane or water? Covalent.
And knowing the rules of nomenclature means you can often tell what kind of bonding is involved just from the name. If you see Roman numerals or just a metal followed by a non-metal ending in "-ide," you think ionic. If you see prefixes, you think covalent.
Exactly. That name instantly gives you clues about its structure and potential behavior. It helps you identify the fundamental process by which a compound was formed. Was it electron transfer between a metal and nonmetal to make ions? Or electron sharing between nonmetals?
So it connects the name back to the why and how of bonding.
Yes, and it gives you the common language needed to communicate about the vast and diverse world of chemical substances accurately and clearly with other scientists, technicians, or even just understanding product labels.
So we've taken a deep dive today into the forces that hold pretty much everything together. We started with why atoms bond, that fundamental drive for stability, trying to achieve that noble gas configuration, often following the octet rule.
Then we saw how electronegativity is the key property dictating how they achieve that stability.
Right, whether it leads to electron transfer in ionic bonds, different kinds of sharing in covalent and polar covalent bonds, the sort of community sharing in metallic bonds, or that special case of coordinate covalent bonding where one atom provides both electrons.
And we wrapped up with why learning the rules of nomenclature is absolutely non-negotiable. It's learning the language that lets us talk about and understand all this incredible variety that comes from just these few types of interactions.
It's foundational.
Absolutely. So considering how deeply understanding these basic principles of chemical bonding, the why and the how allows us to predict and explain the properties and behavior of substances, think about the potential. What doors does this fundamental knowledge open for us? Not just to understand the materials around us.
But maybe to design new ones.
Exactly, to potentially design entirely new materials with specific desired properties, stronger, lighter, conductive, whatever we need. Or, maybe even more profoundly, to truly unravel the complex chemical dance happening constantly within living organisms, which are, at their core, built on these very same bonding principles. What becomes possible when we master this language of connection?